Hi everyone, I'm glad to share our CVPAR work, DBARF, Deep Bundle, Adjusting Generalizable Neural Radiance Fields. Unlike existing works that can only be applied to prior scene-trained NERF, we try to bundle, adjust generalizable NERF without any initialization of camera poses. Once pre-trained, our model can be per-scene fine-tuned in much fewer iterations. Now, let's see how to bundle adjust generalizable NERF. Before that, I'll take a detailed review of generalizable NERF. I'll use Ibernet as an example, but most existing generalizable NERF methods follow a similar pipeline. During training, generalizable NERF selects a target view that the network needs to synthesize and key nearby views. The first step for generalizable NERF is to extract feature maps for the target view and nearby views and project the point of the target view to its nearby views. After obtaining the point features, the second step is to aggregate the pixel-level features for each emitted ray. We denote the aggregation operation by a learnable function FAD. For different generalizable NERF methods, the network architecture of the aggregation function differs. After feature aggregation, we have pure point density sigma and color C. The last step is to do volume rendering. That's a general framework of generalizable NERF methods. Now, it is natural to ask, can we bundle adjust generalizable NERF using the method of BARF? To know this, we conducted an experiment based on a pre-trained generalizable NERF model. Specifically, we pre-train a generalizable NERF model and then fine-tune it on a scene. Following BARF, we constructed an X6 learnable pose embedding. Then, we jointly trained the GenRF and the pose embedding by Atom. The camera poses are initialized by adding very small noises to ground truth. Unfortunately, we found that the camera poses do not converge. Instead, it diverges quickly during the optimization. It suggests bundle adjusting generalizable NERF is non-trivial. Then we may wonder, what are the potential reasons that make bundle adjusting generalizable NERF difficult? We first take the derivative of the loss function UBLRT camera poses. The derivative includes a term for nearby views and a term for the target image. We reveal two main reasons that make the joint optimization of camera poses and GenRF difficult. 1. When points are occluded, the derivative can be wrong since the point features become outliers. 2. Generalizable NERF relies on extracted feature maps. However, the image feature space is highly non-smooth, which can make the optimization of camera poses difficult. We illustrate the first reason in this figure. The feature becomes an outlier due to occlusion. It means that the feature aggregate function must handle inconsistent features. This is difficult. The second reason is illustrated in this right figure. Most existing generalizable NERF methods use resonate as the feature backbone, and we visualized a patch of the extracted feature map. We can find the feature map as highly non-smooth. Instead, in our method, we adopt a feature pyramid network as our feature backbone, and we can see the extracted feature map is smoother than resonate. Based on the previous analysis, we further proposed our solution. We first reformulate the absolute camera poses optimization problem into a relative camera poses optimization problem. After reformulating, we can find we only need to optimize relative camera poses, which in general can be much easier than optimizing absolute camera poses. Based on this equation, we further constructed a cost map by computing the difference between the target feature and nearby features. The cost map is a feature metric error, which has been shown more robust than the photometric error. To deal with outliers, we also adopted a robust kernel row. In our framework, the cost map is deemed as an implicit cost function, and we utilize a gated recurrent unit, GRU, to learn to predict a relative camera poses. To let the GRU optimizer leverage the contextual information, we do not sample points. Instead, we sample a patch that's centered at U. Then, the cost map becomes this. This is the network architecture of our proposed method. The input is images and a scene graph. Nearby views are first selected from a scene graph since the camera poses are unknown. Then, image features are extracted by FPN. In stage A, the image feature of the target view is warped to each nearby view by the corresponding current camera poses and depth, and a cost map is constructed by the image feature difference. Camera poses and depth are recurrently optimized by a GRU, which takes the cost map as the input. In stage B, we utilize a generalizable NERF to predict image color and density value. and the final image is rendered by volume rendering. In Stage C, the pose optimizer and the generalizable NeRF are jointly learned. Finally, our network outputs the posed images. Our method can be trained without any ground truth camera poses. For depth optimization, we adopt the edge. Aware depth maps smoothness loss for self-supervised depth prediction, which can penalize changes where the original image is smooth, where partial X and partial Y are image gradients. For camera poses optimization, we adopt the warped photometric loss for self-supervised pose optimization. We use the same loss of IberNet for training NeRF. We conducted experiments to evaluate our method. The first dataset is the LF forward-facing dataset, which is an outdoor dataset with camera poses facing toward the scene. This dataset provides accurate camera poses. Another dataset is the ScanIt dataset. This is an indoor dataset with imperfect camera poses. Our method is compared against IberNet, DBARF, and GARF. Moreover, our method is trained without using any ground truth camera poses. The quantitative results are given in Table 1 and Table 2. In Table 1, we can see that our method outperforms DBARF and GARF even without fine-tuning. Moreover, our method is comparable to IberNet, which is trained with ground truth camera poses. In Table 2, we show the camera pose accuracy with and without fine-tuning. We also rendered the videos for the LF dataset. As for the scene details, our method can be even better than IberNet. We further visualize the depth images rendered by our trained NeRF model in the pose optimizer. We can observe that while the pose optimizer generates a smoother depth map, NeRF can recover more accurate depth at scene details, especially the thin structures. We believe both depth maps can be improved under self-supervision. NeRF can learn better scene geometry, and pose optimizers can predict more accurate camera poses with better quality depth maps. We also give quantitative results when evaluating our method in IberNet on the ScanIt dataset. Since the camera poses are not accurate in this dataset, our method outperforms IberNet by a large margin. We also show more visualization on the ScanIt dataset. The red rectangle and green rectangle show the scene details after zooming in, and also the generated depth images. That is all of our presentation. Thanks for your listening.